If a black hole entered our solar system, the first sign might not be darkness. It might be a comet. That's the part almost nobody expects. We like to imagine catastrophe arriving with spectacle. A rip in the sky, a glowing vortex, something obvious. Reality would be quieter, disturbingly quiet. And here's the question that matters. Would we even recognize what was happening before the solar system began to loosen? Most people picture a black hole as a cosmic vacuum. Get close and you're swallowed. End of story. But gravity doesn't work like that. If you replace the sun with a black hole of identical mass tomorrow, Earth would continue orbiting almost exactly as it does now. Same path, same year, same gravitational pull. The only immediate difference? No sunlight. Temperatures would plunge. Photosynthesis would stop. Within weeks, the surface would begin to freeze. But orbitally, nothing dramatic. That's the first mental shift. Black holes don't pull harder simply because they're black holes. They pull according to mass. Nothing more mystical than that. So the real threat isn't suction, it's trajectory. Now let's assume something plausible. Not a supermassive object like the one at the center of the Milky Way. I'm talking about a stellar mass black hole, 5, 10, maybe 20 times the sun's mass. The kind formed when a massive star collapses. We now estimate there could be hundreds of millions of these drifting through our galaxy. Most are invisible. In 2022, astronomers identified what appears to be the first isolated stellar mass black hole using gravitational microlensing. They didn't see it directly. They saw a distant star's light bend and brighten as something massive passed in front of it. The object emitted no light of its own. It was found by the distortion it caused. That detail matters, because if one were heading toward us, we wouldn't see a glowing disk in the sky. We would see motion begin to misbehave. The outer solar system would react first. Far beyond Pluto lies the Oort Cloud, a spherical shell of icy debris stretching tens of thousands of astronomical units from the sun. It's loosely bound, fragile in gravitational terms. If a black hole passed within a few thousand astronomical units, those icy bodies would feel it. Their orbits would stretch. Some would be flung inward, and suddenly, the inner solar system would experience an increase in long-period comets, not one or two. A pattern, years of unexpected arrivals. At first, we might blame statistical fluctuation. Then we'd notice something else. The incoming comets wouldn't just be more frequent. Their trajectories would share a subtle alignment, a fingerprint pointing to an external gravitational influence. That realization would be chilling, because by the time the comet storm begins, the intruder is already inside our gravitational neighborhood. Here's where the tension builds quietly. Imagine the black hole passes within a few hundred astronomical units, still far beyond Neptune, still distant in human terms, but in orbital mechanics, that's close. Neptune's orbit begins to shift slightly. Its position deviates from predicted ephemerides. Uranus follows. Saturn feels a gentle tug, and then Jupiter, the stabilizer, starts to wobble. Jupiter isn't just another planet. It's the gravitational architect of the solar system. It shapes asteroid belts. It shields Earth from some impacts. It maintains resonance patterns that keep orbits spaced. If Jupiter's orbit changes meaningfully, stability becomes negotiable. Simulations show that a close flyby of a 10 solar mass object within roughly 100 astronomical units could eject an outer planet entirely, eject into interstellar space. We've observed rogue planets drifting between stars. Many likely began inside stable systems before gravitational interactions cast them out. Now pause for a second. Earth does not need to collide with anything to be lost. It only needs to exchange energy. A gravitational slingshot could increase Earth's orbital velocity enough to send it outward, slowly escaping the sun's pull, or reduce it, causing a gradual inward spiral. Neither outcome is cinematic. Both are terminal. If Earth were pushed outward, surface temperatures would fall steadily. Oceans freeze from the top down. Within years, sea ice thickens globally. Within centuries, the atmosphere begins to condense. If Earth were nudged inward, even slightly, solar radiation increases, climate systems destabilize. A runaway greenhouse becomes possible. Either direction means transformation. And here's something most people underestimate. We would likely have warning, not from seeing the black hole glowing in the sky, but from precision measurements. Missions, like Gaia, track stellar positions with extraordinary accuracy. Planetary radar monitors orbital parameters down to tiny fractions. Deviations accumulate. Models would begin to fail. Astronomers would notice Neptune arriving milliseconds early, Jupiter lagging seconds behind prediction. At first, adjustments. Then, alarm. But detection does not equal control. There is no technology capable of altering the path of a multisolar mass object traveling tens of kilometers per second. You don't deflect it, you calculate around it. Now consider a more intimate encounter. Suppose the black hole crosses the plane of the inner solar system, somewhere between Mars and Jupiter. The gravitational choreography becomes violent. Planets trade energy. Orbits stretch into ellipses. Resonances amplify. Stability erodes quickly. Earth might not be thrown out immediately. Instead, its orbit could become more elliptical. Summers hotter, winters colder, year length subtly altered. Climate feedback. Loops would struggle to adapt, and here's a nuance that rarely gets discussed. Black holes cause tidal forces only when extremely close. A 10 solar mass black hole passing at 1 astronomical unit would disrupt orbits catastrophically, but it would not tear Earth apart. Spaghettification requires proximity on the scale of thousands of kilometers, so destruction wouldn't look like a movie. It would look like a system losing balance. Now let's explore something even stranger: capture. If Earth lost enough orbital energy during the encounter, it could become gravitationally bound to the black hole instead of the sun. Imagine that transition. 1 year, the sun dominates the sky. The next, its angular size slowly shrinks as our new orbit forms around an invisible mass. No sunrise, no seasons, just distant starlight. The black hole itself would remain unseen, unless it accreted gas or debris. Perhaps a faint X-ray glow if material spiraled inward. Otherwise, darkness and motion, because stellar mass black holes travel through the galaxy at tens of kilometers per second relative to nearby stars. If captured, Earth wouldn't simply orbit. In place, we would be moving, rapidly, through interstellar space. The sun would recede. The remaining planets scattered or reshaped. We would become a rogue world. How likely is any of this? Stellar encounters are not imaginary. The star Gliese 710 is predicted to pass through the outer Oort Cloud in about 1.3 million years. It won't disturb Earth directly, but it will stir comets. That's with a normal star. Replace it with a 10 solar mass black hole on a similar trajectory, and the perturbations intensify. Still, encounters within 100 astronomical units are rare. Timescales stretch into billions of years. Statistically, we are safe in the near term. But rare is not the same as impossible. There's another speculative angle worth mentioning. Primordial black holes, hypothetical remnants from the early universe, have resurfaced in theoretical discussions since gravitational wave detections revived interest in unconventional black hole formation channels. If some fraction of dark matter consists of these objects, smaller ones could be more numerous than we expect. A small primordial black hole passing through Earth wouldn't consume the planet. It might pass straight through, leaving a narrow trail of deposited energy. Some researchers have even explored whether unusual seismic signatures could reveal such an event. No confirmed cases exist, but the idea forces an uncomfortable realization. Not all encounters are visible. Not all consequences are dramatic. The universe operates on scales and probabilities that dwarf human intuition. And here's the deeper layer. We tend to think of the solar system as stable because it has been stable during human history. But on cosmic timescales, planetary systems are fluid. Stars migrate through the galactic disk. Gravitational nudges accumulate. Orbits drift chaotically over billions of years. Our sun has likely experienced multiple stellar flybys in its 4.6 billion year lifetime. None were catastrophic. That doesn't mean the architecture is permanent. The most realistic outcome of a black hole entering our solar system isn't immediate annihilation. It's orbital rearrangement. Subtle at first, then decisive. A planet ejected, another shifted inward, resonances broken. Gravity doesn't need drama, it needs time. If such an object were inbound, humanity would not face a sudden flash of destruction. We would face calculations, data updates, revised orbital models, and a growing awareness that the stability we assumed was fundamental is actually conditional. That might be the most unsettling part. Not the black hole itself, but the realization that our entire planetary system is part of a larger gravitational ecosystem inside the Milky Way, one where invisible masses drift silently between stars. A black hole entering our solar system would not be an invasion. It would be physics continuing its work. Mass bending space-time, objects responding, architectures reshaping. And if it ever happens, the sky won't tear open. The comets will arrive first, and only later will we understand what they were trying to tell us.